Welcome to our deep dive on numerical weather prediction. You know, those forecasts we check like religiously to see if we need that umbrella or can finally break out the shorts. But how much do we really know about the science behind those predictions?
What's fascinating is that it's not just about old weather records and gut feelings anymore. We're talking about using complex math and physics to simulate the atmosphere itself.
Yeah, I remember hearing something about that. It all started with a guy named Louis Fry Richardson, right? He wrote this book way back in 1922 called Weather Prediction by Numerical Process. Sounds ambitious.
Ambitious is an understatement. Richardson was a true visionary. He was actually inspired by another meteorologist, Wilhelm Dirknes, who had this grand idea for scientific forecasting.
Okay.
First, you need to gather a ton of data about the atmosphere, temperature, wind, pressure, the whole works. Then you apply the laws of physics to predict how that data will change over time.
Okay, so that's the theory. But Richardson took it a step further, didn't he? He actually tried to put this into practice.
He did, and that's where things get really interesting. His first attempt at a numerical forecast was, to put it mildly, a massive flop.
Oh,
We're talking about predicting a pressure change that was 100 times larger than what actually happened.
hold on, 100 times? Talk about being off the mark. I mean, I get that weather is complex, but that's a pretty spectacular failure, isn't it?
Huh.
What went wrong?
Well, picture this. It's World War I, and Richardson is stuck in a field ambulance unit. Instead of, focusing on his medical duties,
Right.
he's obsessed with this idea of predicting the weather using math. So he divides the atmosphere into this giant 3D grid and tries to solve these incredibly complex equations for each point on the grid.
Whoa, all by hand.
Yep, all by hand. Can you imagine the sheer amount of calculations involved? It took him 6 weeks to produce a 6-hour forecast for just 2 tiny sections of the atmosphere.
6 weeks for 6 hours. That's longer than it takes me to plan a vacation.
Exactly. And the result, let's just say it wasn't exactly front page news in the meteorology world.
Okay, so this gravity wave thing you mentioned earlier, that was the main culprit, right?
Right. Imagine trying to predict the flow of a river while also tracking every single leaf bobbing on the surface.
Mm.
Those leaves are kind of like gravity waves, these fast-moving oscillations in the atmosphere. They're always there, but they don't really tell you much about the overall flow of the river, or in this case, the larger weather patterns.
So they're basically distractions,
Yeah.
like noise in the data.
Precisely.
Yeah.
And because they fluctuate so rapidly, Richardson had to use tiny time steps in his calculations to account for them. This made the whole process incredibly slow, complicated, and prone to errors. It's like trying to write a novel one letter at a time. You might get there eventually, but it's going to be a long and painful process.
That makes sense. So how do we go from this 6-week hand-calculated flop to the forecast we have today, where we can get predictions for the next week in just seconds?
Well, that's where things get even more interesting because while Richardson's initial attempt was a failure, his fundamental ideas were actually spot on. He laid the groundwork for everything that came after.
So he basically planted the seed, but it took a while for it to grow.
Exactly. His work was largely ignored for decades, mostly because the technology just wasn't there to support his vision. But then something big happened in the 1950s that changed everything.
Okay, I'm on the edge of my seat here.
Mhm.
What was this game changer?
It was the arrival of the electronic computer.
Ah.
Suddenly, those complex calculations that took Richardson wits could be done in minutes. And that's when the world finally started paying attention to his ideas.
So the missing piece of the puzzle finally fell into place. It's like having a brilliant blueprint for a building, but waiting for the invention of steel and concrete before you can actually build it. So once computers came along, things started moving quickly, I imagine.
They did. Groups of scientists, particularly one at Princeton, led by a guy named Joel Charney, started building on Richardson's foundation. But even with computers, there were still challenges, right? I mean, those early models couldn't have been as complex as the ones we have today.
Right, so how do they deal with those pesky gravity waves? Did they just ignore them?
Well, they had to find ways to manage them. One early approach was called filtering. Essentially, they modified the equations to try and remove gravity waves entirely from the calculations. Think of it like putting a filter on your camera lens to remove certain colors of light.
Okay, so just pretend those gravity waves don't exist. Seems a bit risky, doesn't it?
It was a starting point, but they quickly realized that ignoring them completely wasn't the best solution. They needed a more sophisticated approach, and that's where things get even more clever. They realized they needed to work smarter, not harder. Instead of filtering out the gravity waves entirely, they focused on adjusting the initial data that went into the models. This is called initialization.
So it's like smoothing out the ripples on that river before you start measuring its flow. Makes sense. But how do you actually smooth out something as complex as atmospheric data?
That's where the real ingenuity comes in. They developed techniques to carefully adjust the initial conditions of the model, minimizing the impact of those fast-moving gravity waves while preserving the larger-scale weather patterns that really matter for forecasting.
That's pretty impressive.
Yeah.
So by the 1950s, we had computers crunching the numbers and clever ways to handle those pesky gravity waves. I'm guessing that's when numerical weather prediction really started to take off.
Absolutely. But remember, those early computers were still pretty limited compared to what we have today. So even with initialization, the models were still pretty basic. They couldn't handle the full complexity of the atmosphere all at once.
So what do they do? Simplify things a bit.
Exactly. They started by focusing on a simplified set of equations that dealt only with the atmosphere's horizontal motion. It was like a first draft, capturing the broad strokes of weather systems without getting bogged down in all the finer details.
So a bit like sketching out the outline of a painting before you start filling in the colors.
A perfect analogy. And even with these simplified models running on those early computers, the results were pretty remarkable. They were able to produce forecasts that were surprisingly accurate, especially considering the limitations of the technology at the time.
That must have been a pretty exciting time for those early pioneers. Seeing their predictions actually coming true, knowing they were building on the work of someone who had been dismissed just a few decades earlier.
It was a major turning point. It proved that Richardson's vision was achievable and set the stage for decades of incredible progress.
So what happened next? Did they just keep adding more and more complexity to the models as computers got more powerful?
Essentially, yes. They started incorporating more physics into the models, adding things like moisture temperature variations and even the effects of the sun's radiation.
So from black and white line drawings to full-color, high-resolution forecasts.
That's a great way to put it. And as the models became more sophisticated, so did our understanding of the atmosphere, its complex behavior. But this journey wasn't without its bumps in the road.
I bet there were some heated debates and unexpected challenges along the way.
You're absolutely right. Numerical weather prediction wasn't just a smooth upward trajectory. There were plenty of dead ends, unexpected obstacles, and even some fierce arguments among scientists about the best way to model the atmosphere.
So even with powerful computers and clever algorithms, predicting the weather is still a tough nut to crack.
It absolutely is. And that brings us to another fascinating aspect of this story, the inherent chaos of the atmosphere. Because you see, even with perfect equations and unlimited computing power, there's a fundamental limit to how far into the future we can make accurate weather predictions.
Wait, are you saying there's a point where even the best supercomputer in the world will just throw its hands up in the air and say, I give up?
In a way, yes. And that's because of something called the butterfly effect. The idea that tiny, seemingly insignificant events can have huge, unpredictable consequences down the line.
Okay, so you're talking about that classic example of a butterfly flapping its wings in Brazil and causing a hurricane in Florida.
Right. It's a simplification, but it illustrates the challenge. The atmosphere is a complex, interconnected system. Even the smallest errors in our initial data, the tiniest uncertainties can lead to vastly different outcomes over time.
So are you saying that we'll never have a perfect weather forecast no matter how much our technology improves?
That's the current thinking. There's a theoretical limit to how far we can predict the weather with any degree of accuracy, even with perfect models. Some estimates put that limit at about 2 weeks.
2 weeks. That's not bad considering we're trying to predict something as wild and unpredictable as the weather. But it also highlights the need for humility, right?
Yeah.
We can make incredible predictions, but we also have to acknowledge that there will always be some level of uncertainty.
Exactly. And that realization that embracing uncertainty was actually the key to making better predictions is what led to some of the most innovative advancements in numerical weather forecasting.
Okay, this sounds intriguing. How do you embrace uncertainty in something like weather forecasting? It seems counterintuitive.
Well, instead of trying to predict a single deterministic future, we've shifted towards probabilistic forecasting. So instead of saying it will rain tomorrow, we now say there's a 70% chance of rain tomorrow.
So it's about accepting that we can't know everything with absolute certainty, and instead focusing on providing a range of possibilities.
Precisely. And to do this, we use something called ensemble forecasting, which involves running multiple simulations of the atmosphere, each with slightly different initial conditions.
So kind of like creating a bunch of alternate realities, each with a slightly different weather outcome.
Exactly. And by analyzing the spread of these different outcomes, we can get a much better sense of the range of possibilities and the likelihood of different weather events.
That's pretty ingenious. So instead of aiming for perfect precision, we're aiming for a more nuanced understanding of the potential outcomes.
That's exactly it. And this approach has led to some significant improvements in forecast accuracy, especially for longer-range predictions. We're now able to provide valuable guidance about potential risks and opportunities weeks or even months in advance.
That's incredible. So in a way, acknowledging the chaos of the atmosphere has actually pushed us towards a more sophisticated and ultimately more useful approach to forecasting.
It really has. And that's what makes numerical weather predictions so fascinating. It's a constant evolution, a journey of discovery. We're learning more and more about the atmosphere every day, and that knowledge is being translated into better forecasts and a deeper understanding of our planet's climate.
So we've got from hand calculations to supercomputers, from ignoring those pesky gravity waves to embracing the chaos of the atmosphere. It's amazing to see how far we've come in just a century. But what about the future of forecasting? What's next on the horizon?
Well, there are some really exciting developments in the works. One area that holds a lot of promise is artificial intelligence, or AI. Imagine a world where AI can analyze massive amounts of weather data, identify patterns we might miss, and even make predictions based on subtle cues that humans wouldn't even notice.
So you're saying AI could help us push past those limits of predictability we were discussing. Could we actually extend that 2-week window?
It's certainly possible. AI is incredibly powerful at finding connections in data that we might overlook. It could also help us make more accurate predictions from limited information, which is crucial for regions where we don't have a lot of weather stations or observations.
That makes sense. I'm thinking about remote areas like the oceans or polar regions where it's really hard to collect data. AI could really fill in those gaps, right?
Exactly. And it's not just about predicting the weather itself. AI can also help us understand the impacts of weather events, like predicting where flooding is likely to occur or identifying areas that are at risk for wildfires.
This is all pretty mind-blowing. It feels like we're on the verge of a whole new era of forecasting. But even with AI and all these advancements, we're still talking about predicting something as inherently chaotic as the atmosphere. Are there just some things we'll never be able to predict with absolute certainty?
That's a great question, and I think it gets to the heart of what makes science so fascinating. We're constantly pushing the boundaries of knowledge, but there will always be some degree of mystery, some element of the unknown. And that's okay. In fact, I think embracing that uncertainty is what drives us to keep exploring, keep questioning, and keep pushing the limits of what we think is possible.
That's a great point. It's not about eliminating uncertainty altogether, but rather about understanding it, quantifying it, and using that knowledge to make better decisions. So where does all of this leave us then? What's the big takeaway for our listeners?
I think the key takeaway is that numerical weather prediction is a journey, not a destination. We've come an incredibly long way since Lewis Fry Richardson's time, but the quest to understand and predict the atmosphere continues. And as we move forward, we're not just improving the accuracy of our forecasts, we're also gaining a deeper understanding of our planet's climate system and the interconnectedness of everything on Earth.
And that's something we all need to be aware of, right? It's not just about knowing whether to pack an umbrella or not. It's about understanding how our actions impact the planet and making informed choices about our future.
Couldn't have said it better myself. So the next time you check your weather app, take a moment to appreciate the incredible amount of science, technology, and human ingenuity that went into creating that forecast. It's a testament to our endless curiosity and our desire to understand the world around us.
Well said. Thanks for taking us on this deep dive. It's been an eye-opening journey through the world of numerical weather prediction. And to our listeners, stay curious, keep exploring, and remember that even when it comes to something as complex as the weather, there's always more to learn.